Okay, so welcome to Chemistry 101. We're doing Chapter 8 and 10, Chapter 10 Selected Problems. We will be skipping over Chapter 9 for this course. Which type of elements are most likely to form compounds using ionic bond? So we've kind of touched on this when we were talking about naming. So ionic bonds have metals with nonmetals. And so 2/3 of the periodic table are metals. And so if they begin with a metal, then we got to deal with charges. The metals will give up an electron and form positive ions, which we call cations. And the anions will take those electrons and form negative charges, which we call anions. And together, this electrostatic attraction is ionic bonding. And you'll find ionic bonding compounds tend to have the highest melting points and boiling points. So which of the following are likely to have covalent, so what type of elements are most likely to form compounds using ionic bonds? And the answer is metal with a nonmetal. Okay, next question. Which of the following compounds are likely to have covalent bonds? These are nonmetal with a nonmetal. So H can be weird because, and you'll see on your periodic table, it can be in group 1 or with the metals, or it can be in group 7 with the nonmetals. Hydrofluoric acid, so you're going to start learning how to draw these structures. If it is in the gas phase, then it's going to be covalent. If it's in the aqueous phase, then it's going to form its charges, and that will be so that one's now sodium. Sodium is without a doubt a metal, and so you got a metal, and then you have a nonmetal. So this would be ionic. So this can do both depending on the phase. NCl, this is a nonmetal with a nonmetal. I'm just going to call that NM, nonmetal. So this is covalent for sure. Magnesium is a metal. So metal with a nonmetal, that is going to be ionic. Carbon with fluorine is a nonmetal with a nonmetal. So the two of these would be NCl3 and CF4. Identify the bonding in each of the following is ionic or covalent. Calcium is a metal, so you got to, anytime you have a metal, you can just go ahead and say that's going to be ionic. This is a nonmetal with a nonmetal, it's diatomic, and that's going to be covalent. This is a nonmetal with a nonmetal, this is covalent. And iron is a transition metal, so you know that's going to be ionic. Which of the following compounds are likely to occur as gases at room temperature? Okay, so gases at room temperature are going to be covalent compounds. So once again, you're looking for the nonmetal with the nonmetal for gases at room temperature. So KBr is a metal, so that's going to be ionic. HCl, if it is a gas, then that would be room temperature, because H in that case would be acting as a nonmetal. SF4, you can see that sulfur is a nonmetal. So this is a nonmetal with a nonmetal, so that would be covalent. Calcium is in group 2, so that's a metal. So that will not, that's an ionic compound. And this is methane with carbon being a nonmetal. So it's a nonmetal with a nonmetal. So those would be gases at room temperature. Predict whether each of the following substances is likely to have a relatively high or low melting point. Okay, so if you have a high melting point, I'm just going to do MP for melting point, that's going to be an ionic compound. So the low melting points are your covalent compounds. So the high ones are going to be, you got a metal here, and aluminum is a metal, so that will be high melting points. Calcium is a metal, so that will be high. And so your low melting points are your nonmetal with a nonmetal. So this is covalent, carbon tetrachloride, and then phosphorus with itself, that is a nonmetal with a nonmetal, and that's going to have a low melting point. Describe how electronegativity values change going down a group in the periodic table. Okay, so electronegativity is, so whenever you have a bond, like a covalent bond, a covalent bond is they share electrons. So two elements are sharing electrons, like carbon and oxygen. And so they're sharing those electrons, and the more electronegative element will pull the electrons towards itself. And so you can do this like this, where carbon becomes partially positive and oxygen becomes partially negative. So it's like a tug of war. And that electron density is going to be pushed towards the more electronegative, we'll just write En, element. And this is very important because this is going to determine a lot of our intermolecular forces. So you need to know the trends. So increasing electronegativity goes up a group and to over a row. So the highest, you can look at your tables in your book, the highest is fluorine up here in the upper right hand corner, and it has electronegativity value of 4.0. The lowest is francium, and what is this number? You don't have to memorize these numbers. You do need to know the trend. So when you see two elements, this is on figure 8.5, and francium is 0.7. So that's going to be your lowest electronegativity element. So whenever these two elements are in a bond, then which one's going to win that tug of war? You can see that carbon has a value of 2.6 and oxygen has a value of 3.4. So 3.4 wins, and those electrons, and these are electrons in this arrow, are going to push towards the oxygen, leaving carbon slightly positive. You don't have to memorize those numbers, but you do need to have this trend memorized. So using periodic trends, arrange the following atoms in order of increasing electronegativity. Okay, well, you got to get out your periodic table. And you see boron, carbon, hydrogen. Okay, so selenium is, and silica. So the lowest is selenium. So selenium would be the least electronegative, because selenium is like right here, and selenium is below sulfur, and silica is right here, so I would say this is less. So I'm going to put my small mouth of my gator mouth, and then silica, and then I would say hydrogen, and then I would say boron, and then carbon. Now I can look at these numbers and see if I'm right. So the number for silica is 1.9, and selenium is 2.6. So I did have those wrong, so this should be Si or Se. Hydrogen is 2.2. So this one was, so let's put hydrogen here and then selenium. And then boron is 2.0 and carbon is 2.6. Now what I'll normally do, if you don't have access to these values, I would make sure they're either all in the same group or they're all in the same row, so you can apply your trend. Okay, what about this one? Well, I can tell you calcium is the least, and cesium. Actually, cesium is a metal in the first group, so it's going to be less than calcium. And I would say copper because it's a metal. And then between carbon and chlorine, I would say um, carbon and then chlorine. Now these are all over the place, so I'm going to look these values up. Chlorine is 3.2 and carbon is 2.6, so I'm good there. Copper is a metal, so it's going to be less than the non-metals, 1.9, and calcium is 1.0, and cesium is 0.8. So metals are going to have a lot less low electronegativity compared to nonmetals. So when you get into this part of the periodic table, these are going to have really high electronegativity values, and these are going to have very low. Decide which bond in each pair is polar and explain your reasoning. Okay, so H and H, so you can look at these numbers and then you subtract the difference. So sometimes you'll see this means delta, a triangle. Difference in electronegativity, so 2.2 minus 2.2 is 0. And so this is pure covalent, meaning the electronegativity difference is 0. You only have that when something's bonded to itself. HF, well, you got a 2.2 for hydrogen, and you got a 4.0 for hydrogen. So clearly, that is what you want to draw the dipole. So when it asks for the dipole moment, you want this, where you show where the positive is and towards the push of the electrons. Another way you can do that is you could do this delta positive and delta negative. Okay, so ClCl, well, you should know that that is going to be 0. That's pure covalent. And you can even look those numbers up. 3.2 minus 3.2 is 0. Now, this one, where's iodide? Iodide is below. So they're in the same group. We get chlorine and iodide. So I would say chlorine is more electronegative based on the trend. So you might want to draw your dipole moment like this, or you could do a delta positive with the iodide and delta negative with the chlorine. Looking at your actual numbers, iodide is 2.7, and chlorine is a 3.2. Once again, HH is pure covalent, and boron and H, boron is 2.0 and H is 2.2. So in that case, H is up here with our kind of like a group 7 non-metal, and that would be your dipole. Draw Lewis structures showing the valence electrons of the following atoms. Okay, well, we talked about what groups they are. So these are the electrons that they can contribute to bonding. You need to, first thing you're going to do when you're doing these structures, and it's very important to start learning how to draw Lewis structures, is to count up all the valence electrons that go into that. So carbon is in group 4A, so it has 4, and when you draw the Lewis structures, you just draw it around carbon like that. Iodide is in group 7A. A is the representative metals. We're not transition metals, or B. Okay, so we have 7. So 1, 2, 3, 4, 5, 6, 7. Selenium is in group 6A. So 1, 2, 3, 4, 5, 6. You just kind of go around in 4 places. Cesium is group 1A, so it gets 1 valence electron. Strontium is 2A, so it gets 2. Argon is in group 8A. It has a complete octet. It will not participate in bonding because it's a noble gas and it has a complete octet, and it has 8. Okay, so draw the Lewis structures for oxygen and fluorine. Well, the first thing you need to do is you need to count up your total electrons. So oxygen has 6 valence electrons, and there's 2 oxygens because of the subscript. So it has 12 valence electrons. So that's always step 1, total valence electrons. Step 2 is connectivity. So you got to see how they're connected to each other. So here we do oxygen and oxygen. And then step 3 is you add the electrons. Add all the valence electrons, and you got to try to fix an octet. So when you draw a line like this is a bond, and a bond has 2 electrons. So you've used 2. You have 12. So you've already used 2. So you go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you want to go outside and then go in. So you want to work outside in, and you want to put them in pairs. And then the last thing you want to do is check your octet. Octet means in row 2, each has to have 8. So this has 1, 2, 3, 4, 5, 6, 7, 8. So that has 8. So that octet is fine. Let's look at this oxygen. It has 1, 2, because it gets to share that. 1, 2, 3, 4, 5, 6. 6 valence electrons. It is so unhappy. Okay, so what you want to do then is you want to take a pair from the 8 and you want to make a double bond between the 2. And so then you need to redraw. And then we'll have to check for the octets. So now we have a double bond. And then everything else is the same. These 2 are here, those 2 are there, these 2 are here, and these 2 are here. So now we'll count to make sure there's an octet. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is the structure of oxygen. Okay, so how many valence electrons are around each atom in these structures? So we've been doing that. So we did 12 valence electrons for oxygen. What about fluorine? So fluorine is group 7A, and there's 2 of them. So 2 times 7 is 14. So 14 valence electrons. Describe the bonding each as a single, double, or triple covalent bond. So oxygen has a double covalent bond. And you can say that in this structure you have 1, 2, 3, 4 lone pairs. Now what about fluorine? Well, so we have 14 valence electrons, and then we're going to connect fluorine like this. Okay, so now this is 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So we have 14. And then you check and you count 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. So each one of these are fine. Now, I'm going to tell you, fluorine has a single covalent bond, and that will be always. So hydrogen and fluorine can only do a single covalent bond. I'm going to say always. So if you ever have hydrogen and fluorine bonded to 2 things, it's wrong. If you ever have hydrogen and fluorine double bonded, it's wrong. Hydrogen and fluorine can only do single bonds. Okay, so how many single bonds are typically formed by the following atoms? Now I call these my happy atoms. Okay, my happy atoms. See my happy face? Happy atoms. And when I'm trying to figure out connectivity and what the structure is, I have this as my go-to, because hydrogen will form 1 single bond. Nitrogen will form, well, let's just not skip over all of them. Let's go across. So we have, your metals are going to form plus charges, so they're not doing covalent bonding. So hydrogen participates, you have one single bond, you have 0 lone pair when you have happy atoms. Okay, then you go over to boron. Boron likes 3 single bonds, and it likes 0 lone pair. And then you get to carbon. Carbon likes, and I'm not going to say single, but I'm going to say 4 covalent bonds. Covalent bonds. And it actually likes 0 lone pairs. Okay, that's what makes it the happiest. Nitrogen likes 3 covalent bonds. No, that's not true. It likes 1 covalent bond and 3 lone pairs. And then oxygen likes 2 covalent bonds and 2 lone pair. And fluorine likes 1 covalent bond and 3 lone pair. So you see this? So we got one bond and 0 lone pair, and then we're going to do 3, 4, 1, 2, 1. I'm sorry, this should be, I'm getting tired at the end of the day. Okay, I was right. This should be 3 covalent bonds and 1 lone pair. So it goes 1. So we have hydrogen, boron, carbon, nitrogen, oxygen, fluorine. And so we're going to do the bonds, covalent bonds, and then we're going to do lone pair. This is 1 and 0. This is 3 and 0. This is 4 and 0. This is 3 and 1. This is 2 and 2. This is 1 and 3. So do you see a pattern? Do you see how you go from 1 and then 3, 4, so you're moving up, and then you go 3, 2, 1. You go down across the row. And then here you go from 0, 0, 0, and then 1, 2, 3. This will be helpful at some point. Okay, so how many are typically formed? 1. Nitrogen. This is nitrogen. So I do 3 covalent bonds and 1 lone pair. Fluorine, I would say 1 single bond and 3 lone pairs. Neon is 0. Neon does not participate in bonding. Draw the Lewis structures of each of the following. Okay, so these are, you want to total up your valence electrons. So you have 1, because it's group 1, plus 4, plus 5. Because carbon is group 4, nitrogen is 5. So that's 10 valence electrons. The connectivity, when they're written like this, that is your connectivity. So you can connect that like that. And now we can count up, we got to add our valence electrons. You have 1, 2, 3, 4. Let's go outside in. 3, 4, 5, 6, 7, 8, 9, 10. Okay, so you see that nitrogen's okay. Hydrogen only needs 2 for its octet, but carbon only has 4 and it needs 8. Now you can just go with straight here, which nitrogen likes 3 bonds. So you could just draw it like this. Nitrogen is going to have 3 bonds and 1 lone pair. And then hydrogen likes 1 bond with 0 lone pairs. And then carbon likes 4 bonds, 1, 2, 3, 4, with 0 lone pairs. If you can't memorize this and do this, then you could take these here and then redraw, and then you're going to see that carbon now has 6, and you take this and then redraw. Okay, now working on our next one here, this carbon has hydrogen bonded to, there's 3 of them. Now hydrogen can only do a single bond, so this is that section here. And now this is bonded to carbon and is bonded to nitrogen. Now, You can go straight to the nitrogen, has 3 bonds with 1 lone pair, and then carbon has 4, 1, 2, 3, 4 with 0. And so this is your structure with the connectivity. What you can do is you can add 3 valence electrons plus 4 plus 4 plus 5, and then you get 8 plus 8 is 16 valence electrons, and then you need to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, so you use 16 valence electrons, and each octet is complete. Okay, here you have carbon connected to carbon, and then you can put a hydrogen on each one of these. There's multiple ways, or you can do carbon, carbon. Well, that's probably the best way to do that. And now you can follow your carbon has how many bonds? 4. So 1, 2, 3, 4. And this is called acetylene, and there's 4. So count up how many you got. You have 2 times 4 is 8, and then plus 2. So you have 10 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 10 valence electrons, and each octet is satisfied. C2H4, you'll want carbon to be connected to each other, and then I would just distribute the 4 hydrogens between the 2 carbons. And then you see that hydrogen has the 1 bond with 0 lone pairs. Carbon needs 4, 1, 2, 3, 4, so you can do that. You can add your valence electrons. 4 times 2 is 8. 8 plus 4 is 12 valence electrons. And you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so here we have NO3. This is nitrate, which you've already learned, and it has a negative charge. So if you added your valence electrons, nitrogen's group 5, oxygen is group 6, and there's 3 of them, and then you got to add the 1 for the charge, the negative charge. So total valence electrons would be 18 plus 6 is 24 valence electrons. And the way these work is nitrogen will be connected to the oxygen. So you're going to have 3 oxygens here. Connectivity, nitrogen's in the center. And then you're going to have to count 24 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And then the problem is you see nitrogen needs another bond because nitrogen only has 6 valence electrons, which makes it sad because of the octet rule. So then you're going to take one of these and share. So you're going to redraw that. And in that case, then you can do the negative. Let's move these out of the way so we can have some working space. Okay, sulfate. So sulfur is 6, oxygen is group 6, there's 4 of them, plus the 2 for the charge. So you got 6 times 5 is 30, plus 2 is 32 valence electrons. You have sulfur connected to 4 oxygens. And then you can add your electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. And then everything satisfies the octet, so then you just do that. Okay, what about NO2? You have nitrogen is group 5, oxygen is group 6, and now you have a positive charge. So you're going to take 11 and then you're going to subtract an electron because for the positive charge. So you have 10 valence electrons to work with, and here you have the connectivity. And I would just go ahead and maybe do a double bond, or I would do you could even do a triple bond, because nitrogen likes 3 bonds with the 1 lone pair. And then you can say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you can say, okay, there you go. And you'll see that you follow those patterns we talked about, the bonding patterns, you'll see that you'll get your octet closer sooner. Indicate whether or not each of the following molecules or ions exhibit resonance. So resonance means you can move those electrons around. And so the only ones that can move electrons around is if you have lone pair next to a double bond or a triple bond. A single bonds, the ones that connect the atoms together, we call those sigma bonds. And they hold the elements together, and they have no resonance. If you get compounds that have lone pairs next to double or triple bonds, then absolutely resonance. So oxygen, which you saw has a double bond, and so you see there's a lone pair next to that double bond. So what can happen then is those lone pairs can go make a triple bond or something, and so then in a resonance arrow, it's like a double-headed arrow, and you can form something like this. Actually, you can't do that. Why? Because that's an octet violation. We cannot have octet violations. So in that case, not on the same element. So let's just correct this. There is no resonance here because you don't have next door, next to. In this case, the lone pair is on the same element as the double bond. So it has to be next to. So let's just highlight the next to. It has to be next to the double bond. They have to be 2 different elements. 2 elements. Okay, so let's look. Water, if you do that structure, you'll see that this is water. You'll see that there's no double or triple bond, so that's a no resonance. SO2, how many valence electrons do you have? 6 times 3 is 18. Okay, so you have that here, and then you just go ahead and do the double bond. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Sulfur can do a thing called expanded octet. And so this is only for row 3 or higher. They can have greater than 8 electrons because they have these expanded orbitals. They're bigger. They're bigger. They can hold extra electrons. So in that case, do you have 18? 6 times 3 is 18. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. The reason why this cannot do resonance, well, and I'm going to say no, because you can't push electrons onto the oxygen, because you can't do expanded octet there. Let's do the SO3. And this is 2 minus, so here we have 4 times 6 is 24 plus the 2, so 26 electrons. So here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So you always put those extra ones on that. So there's your 2 minus. Now, the reason why this can, I'll do the double-headed arrow, is because oxygen here has a single bond, but it likes 2 bonds. So those 2 electrons can go there, and then those electrons can go there. So it can go to this structure. And see how the lone pair turned into a new pi bond? And then we can do it again. We can take, oh, well, don't forget your lone pair here. We can take this pair here, turn that into a pi bond, and then move that pi bond into a lone pair. And then that looks like this. And that was these electrons here, and then those electrons went there. And every octet, except for the expanded octet, follows the octet rule. And every oxygen can have a chance to have a double bond. And so in that case, you do have resonance structures. And when you do that, then I look at that and say, oh, okay, so you can have multiple correct answers. Describe whether the indicated atom obeys the octet rule. So oxygen and water. Oxygen must always obey the octet rule. Okay, so that means it will have 8. Sulfur and S4, SF4. Well, sulfur 6 and fluorine is group 7. There's 4 of those, so that's 28. 28 plus 6 is 34. Fluorine always has to be terminal because it can only have a single bond and it has to have 3 lone pairs. So before we even count any electrons, this is how fluorine has to be, because fluorine cannot not obey the octet rule. So let's see what we have here. We have 8 times 4 is 32, and then the extra ones here will have to go on sulfur. So that is expanded octet for sulfur. Sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. So sulfur does not obey, and it is expanded octet. What about S and F2? So we can do this, and you know you're going to have fluorine like this. Now let's count them up. 6 plus 2 times 7. So that's 14 plus 6 is 20. We have 8 times 2 is 16, 17, 18, 19, 20. And you cannot make a double bond. So let's count how much sulfur gets. 1, 2, 3, 4, 5, 6, 7, 8. So yes, this obeys the octet rule because it's 8. Fluorine and SF4, we just did that one here, and it will always obey. Fluorine will always obey, or else your structure is incorrect. What are the different classes of hydrocarbons? Okay, so when we need classes of compounds, these are your organic compounds, okay? So these are organic. Organic means of the organ. And so this is in your body, and these are carbon compounds. So we're going to be doing a lot of Lewis structures with carbon compounds, and then we have to classify them. And you'll see a functional group in your reading, functional group. And that's because classes of compounds will behave similarly, and they'll have similar physical properties and similar chemical properties based on their functional group. Hydrocarbons, there's 4 classes of hydrocarbons. There are the alkane, the alkene, E-N-E, and the alkyne, and the aromatic. An example of an alkane is your gasoline, octane, and this is propane. So propane gas, propane, see the A-N-E, alkane, they're just single bonds. So hydrocarbons have hydrogen and carbon, so only hydrogen and carbon. You don't see any other element in these compounds, just hydrocarbons, and there's 4 classes. Alkene has a double bond, so you'll see a double bond. The ripening reagent is ethene. Okay, so this is called ethene. Bananas will give off this ripening reagent, and it causes all the other fruit to ripen. Alkyne is a triple bond. So the world is full of alkynes, all kinds. So this is called acetylene. We'll also call it ethine, YNE. This is what's used as a gas. It gets very hot for welding. Aromatic is like benzene. Now, you don't know the stick structure. Okay, so carbon, carbon. So you got to have a ring, and you have to have alternating single and double bonds for it to be aromatic. So double bond, single bond, double bond, single bond, double bond. And so you have a ring, and this is an aromatic compound. And this is the Lewis structure for benzene, C6H6. Identify the class of organic substance for each of the following molecules. Okay, so you need to kind of get in the habit of drawing these out. So you see that you have 3 hydrogens. That means those 3 hydrogens go on that carbon, and then that carbon's connected to that oxygen, and that hydrogen's connected to that oxygen. And then oxygen likes 2 bonds and 2 lone pairs. So this is the Lewis structure. Now that's an OH. This is methanol, and this is an alcohol. So it's always going to be what's connected to the carbon. So this is the oxygen. And then oxygen likes 2 bonds. So oxygen forms 2 bonds. 2 bonds and 2 lone pairs. So one of the oxygens will always be bonded to the carbon. So you need to see what else is it bonded to. So here, if it's bonded to an oxygen and a hydrogen, that is an alcohol. Okay, let's look at this one. Carbon, those 3 hydrogens are bonded to the carbon. The oxygen is in the middle, and then the 3 hydrogens are bonded to the carbon. Now this oxygen is bonded to 2 carbons. You see this? Because you know it's always going to be bonded to one of the carbons here, but then what is it over here? Well, it's another carbon. And so when it's not a hydrogen, because if it's a hydrogen, it's an alcohol. But if it's an oxygen, if it's another carbon, it's an ether. So it's an ether. Okay, in this case, we have carbon with 3 hydrogens bonded to another carbon. This is an hydrocarbon because there's no oxygens there. There's no heteroions, just hydrocarbons, hydrogen and carbon, only single bonds. This is an alkane. Here, there's no heteroatoms. Heteroatoms are anything other than hydrogen and carbon. There's just hydrogen carbon. I'm going to draw your structure here so you can see it. You have a double bond. You'll see that carbon follows the octet. This is a double bond here, and that is called an alkene, E-N-E, alkene. All right, the next one we have here is carbon has its 3 hydrogens, and then this is bonded to this carbon. And now, when you see something like this, this is actually a double bonded oxygen, and then you got carbon with the 3. So in this case, these 3 hydrogens go onto that carbon, so this is going to be a double bonded oxygen. this is a carbonyl, the C double bond O. And of the carbonyl, you've got different functional groups. You can have aldehyde, you can have ketones, you can have carboxylic acids. So this carbonyl is always going to be doubly bonded to the carbon, but you got to look at what's this carbon connected to, the one that's the carbonyl. What is it connected to? Well, you see this is bonded to another carbon and another carbon. It's always going to be bonded to one carbon. So if it's connected to the other carbon, it's called a ketone. So this is a ketone. Draw the Lewis structure for an aldehyde that has the molecular formula C4H8. Oh, aldehydes always they form double bonds to the carbon, and then that carbon is going to be bonded to a carbon, but the other carbon has to be an H. Okay, so this is an aldehyde. So it's always going to be at the end because the H has to be terminal. And how many do we have? 4 carbons. So we have 1, 2, 3, 4. Think of a choo-choo train. And then you just want to fill in to make it 4. So carbon gets 4 bonds. So 1, 2, 3, 4. This already has 2, so add 2 more. You got 2, add 2 more. Let's see if that works out. C4, 3, 4, 5, 6, 7, H8, and 1 oxygen. So this is an aldehyde. Predict the shapes and give approximate bond angles for the following molecules. Okay, so some of these are inorganic, meaning not carbon. So beryllium, so we're going to do the total valence electron, and then we'll do connectivity. So beryllium has 2 because it's group 2, and then chlorine has 7, and there's 2 of them. So that's 14 plus 2 is 16. And so beryllium is going to be in the center, and then you got chlorine, and then you got to do, we're going to count 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And so beryllium doesn't have a complete octet there. Beryllium is one of those weird ones. This is going to be linear. And the approximate bond angles, you just have to remember that. And that is how far are these related to each other. That's 180 degrees because it's linear. Okay, pH 3. Well, phosphorus is group 5, and then we have 3 times 1. So that's 9 valence electrons. Phosphorus will be in the center. And so we have those. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I think it's 8, isn't it? Yes, 8. 3, 4, 5, 6, 7, 8. Okay, so this has 4 things. And if I look in your book in chapter 8 for the geometry, so you might want to bonding in carbon compounds. Okay, so you want to look at Vesper and the different structures. Look at table 8.5 and 8.6. So when you have lone pairs, so we're looking at 8.6. So the electron domains, there's 4 things. We're always looking at the central atom. We just care about the central atom when we're predicting shapes. So here's the central atoms. There's 4 things because a lone pair is a thing. And those are called electron domains. So if you go to that chart, you see 4 domains. Okay? So that would be, but you have 1 unshared electron. So what's going to happen is it's going to push all of these down. And so when you have 3 bonds and 1 lone pair, it's going to make that trigonal pyramidal. So it's going to push, like the phosphorus, this is your P, it's going to make a pyramid. And it's the lone pairs are going to take up the most. So this is a trigonal because there's 3 hydrogens there, right? And so it's trigonal pyramidal. Okay, BBr3, when you draw your Lewis structure, you should get this into your lone pairs. And you're just going to look at that central atom, and you have 3 things. And you have no lone pair, 0 lone pair in those things. So that's going to be trigonal, because it's 3 things, but that's planar. So it's going to be flat like a piece of paper. So you see the 3 and 0 is trigonal planar. Okay, SCl2. And this is really double bonded here. And we can count up our valence electrons. So you have 7 times 2 is 14, plus 6 is 20. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So let me do that. All right. So here we have 4 things, because we count the lone pairs, and we don't count the double bonds. You know, basically, what are our 4 things? Our 4 things is this is 1 thing, this is 2 things, this is 3, and that's 4. So you go to 4 things, but you have 2 lone pairs. So these are 2 lone pairs. So 4 is tetrahedral, but once you get the 2 lone pairs, this is going to be bent. So what's going to happen is those lone pairs are going to hang up here, and they're going to push the Cl together. So what you want to do sometimes is just imagine what that would look like without those lone pairs, and then that would be linear, and then it gets bent. SO2, we have 18 valence electrons. So let's see what we got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So you see you have 3 things, 3 electron domains, and then you have 1 lone pair. So that's 3 and 1, and that's going to be bent. And maybe you could see that because you have 2 oxygens with sulfur holding on to the oxygen, but then the lone pair is going to push everything away because electrons repulse each other and they take up a lot of space. Okay, Si silane. So you have silica is 4 plus 4, that's 8 valence electrons. And so this has 4 things, 4 electron groups, 0 lone pair. So we're going to call that tetrahedral. Oh, you want the bond angles? You base that on the tetrahedral. So that's 180 degrees. In this case, this would actually be 4 things. So the tetrahedral, but then you would say less than 109.5 degrees. Tetrahedral, I'm sorry, is 109.5 degrees. You do have to memorize that. Linear is 180. Trigonal pyramid, trigonal planar is 120 degrees. Are the following molecules polar or nonpolar? So what you're looking at now is you draw the Lewis structure and then you look and see if it has symmetry. So HI, well, there's no symmetry there. That's basically pushes the electrons towards iodide. That would definitely be polar because there's electronegativity difference. CHF3, well, there's not symmetry there because the hydrogen is not a fluorine. And so each one of these are going to pull the electron density towards itself. So overall, your electron negativity is going to be going, if you add these vectors, in a direction towards the fluorine, and this makes it polar. Okay, SO2Cl. So I would say you're dealing with something like this, and we're going to have to add those valence electrons. So we have 6 plus 12 plus 14. So 6, 7, 18, and 14, 8, 9, 10, 11, 12, 32. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Anytime you have a lone pair, you're going to have polarity. So that's going to be polar. Okay, PF3. So fluorine can only do single bonds. So we're going to start there. And then we're going to add phosphorus is 5 plus 7 times 3 is 21. 21 plus 5 is 26. So we have 8 times 3 is 24, 25, 26. Once again, we have a lone pair, so this is going to be polar. For each pair of molecules, decide which molecule is polar and explain why it is polar and why the other is not. Okay, so SO2. And let's see how many valence electrons we have. 6 times 3 is 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Polar. Has a lone pair. CO2. I know carbon likes 4 bonds. Oxygen's 2 and 2. So we have 4 plus 6 times 2 is 12. So 16, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, now you notice that this would pull electronegativity that way, and then this would pull electronegativity that way, and they would cancel each other out. That's that. When I say that's nonpolar, that means the dipole moment is that means that a cursive U is 0 Debye, D is Debye. So that is nonpolar, because it would cancel it out because there's symmetry. Okay, so we already have SO2 here, so we already know that that's polar. Now we're going to do SO3. Oxygen cannot break the octet rule. So now we have 6 times 4 is 24. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Do you see that there's symmetry there? So that would be nonpolar. And it's because there's symmetry. All right, so CH4 is methane. So there's symmetry there. This is nonpolar. And then we have CH3, and then you have iodide here. And this would push that way, and that would be polar. There is a dipole moment. Compare and contrast liquids and gases at molecular level. Okay, so at the molecular level, and it's just about how close they are together. So if you have, let's say, so this is a liquid, and they're kind of close together, and so they can have these intermolecular forces. That's what we're talking about, intermolecular forces. And intermolecular means between the molecules. It's like, are they sticky when they get close together? When you add heat, then what happens is that they move further apart from each other. Okay, and when they move further apart, they're still the same. They're just moving further apart, and then they can't interact with each other. They can't feel each other's intermolecular forces. So they have less IMF. So we'll call this intermolecular forces. They're too far apart. Here they have intermolecular forces. So when you're doing this phase from a liquid to a gas, this is the boiling. And we have to add so much heat. So depending on how strong, so the question is, how strong are these intermolecular forces? Because if you want to separate them, which you do in a phase change, so when you go from a solid to a liquid to a gas, you're trying to separate these intermolecular forces. So we're going to talk about what these intermolecular forces are. You've already seen them with ionic bonds versus covalent bonds. So if something has an ionic bond, they have electrostatic intermolecular forces. And you know that plus minus, that's why they have high boiling points and high melting points, because it takes a lot of heat energy to break apart that intermolecular forces. For covalent compounds, you have hydrogen bonding, and we'll talk about these, is the highest. And then we have dipole-dipole, and then we have dispersion. So you have 3 of these, and then we'll rank those. Is evaporation exothermic or endothermic? So evaporation is going from a liquid to a gas. So you have to put heat in. So you have to put heat plus the liquid. So that would be an endothermic process. Describe how energy is involved. So you have to put heat in. Picture of a change of state, problem 10.31. Okay, so I'm going to go to 10.31, and I'm going to draw your phase change temperature diagram, and this is heat removed. And I just want you to be able to label these. So if we have A, and we go down, and we have B, and then we have C, and then we have D, and then we have E, and then we have F. All right, so the picture change, and then they give you this picture here with these molecules. And then you have a few of them that are up here in the gas. So this is the gas phase. And this would be your liquid. So some of these little molecules here have gotten enough energy, they overcame these intermolecular forces that are holding these molecules together. They got enough heat. This is like boiling water. So where would this change of state occur in the cooling curve? Well, A has to be right here. This is pure gas phase, because that's a higher temperature. See, this is higher temperature. You could say this is 100 degrees Celsius. You can think of this as like water. Okay, so if that's gas, this would be the liquid, and then this would be the solid. So where are these at? These where would this one be? This would be the process of going from one to the other. So in this case, this would, when you go from gas to liquid, you are condensing. When you go from a liquid to a solid, you're so you go this way, you're melting, and this way, what would you be doing? So here you'd be boiling. So this would be condensing from a gas to a liquid, and from a liquid to a solid. I'm lost for words right here, so I'm going to go and look. Um, well, I can see it right here. Condensation, we've talked about that. Evaporation goes from a liquid to a gas. You know what melting is? We just have to look it up. Freezing? Yeah, that would be freezing. I don't know why. Couldn't think of that. Well, anyway, what change of state would occur in the diagram to match the picture? So this would be going to the gas phase. So this would be all gas. So this would be A. So, or actually it would be B, because you're right there. So you have these three gas molecules, but most of it is the liquid, so the process. What is meant by the term of intermolecular forces? Intermolecular forces are the forces that are felt or they're attracted between molecules. And so, like I said, you got for covalent bonds, you have hydrogen bonding. They cost the most to overcome. That's why water, with its only molecular weight of 18, has a boiling point of like 100 degrees Celsius, which is huge. And it has two hydrogen bonding. So, and then you have dipole-dipole. So if you have a polar molecule, that's what you have here. Polar molecule. You're going to have dipole-dipole. And then dispersion is what you have from nonpolar molecules. So like your hydrocarbons. Hydrogen bond, you have to have a hydrogen and either an oxygen, nitrogen, or fluorine. Okay, that's what it requires for hydrogen bonding. So which of the following molecules can experience dipole-dipole? Well, carbon dioxide, if you draw the Lewis structure, you would see that it's nonpolar. So this would be dispersion. So no dipole-dipole. NO, so we have NO, let's see, we have 5 plus 6 is 11. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That is not 6 plus 5, is that 11? Yeah, 11. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I think we need to make that a plus. So let's make that 10. Make that a nitro plus. Okay? Because we can't break the octet there. So that might be a typo. Okay, you see you do have a dipole moment, so I'm going to go with yes, dipole-dipole. NF3, you see how we just drew in a lone pair for the nitrogen? So that's a yes, because that means it's polar molecule. And this one is also a polar molecule because there's some pull there with the chlorine. So that is a yes, dipole-dipole. Which of the following pure substances can participate in hydrogen bonding? So let's go back up to the requirement here. So here we have water. And is the hydrogen connected to the oxygen? Yes, so that can do hydrogen bonding. And you have to have also a lone, well, you were going to have a lone pair. Okay, nitrogen right there. So you got hydrogen and nitrogen. So this is yes. This is ammonia, Mr. Clean. Selenium with H. And selenium has 6 valence electrons. So 6 plus 2 is 8. So 1, 2, 3, 4, 5, 6, 7, 8. And you have a hydrogen, yes, but you have to have oxygen, nitrogen, or a fluorine. So this is a no. No hydrogen bonding. Okay, which of the following substances can form hydrogen bonds with water molecules? Now this is about solubility. So if it can form hydrogen bonds with water, that means it's soluble in water. So for it to be hydrogen bonds with water, it has to have a hydrogen. It has to have a hydrogen. Okay, so HF can form hydrogen bonds. Beryllium can form hydrogen bonds with the water, and this does not have, let's see, what's that? 14 plus 6 is 20. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. It doesn't have a hydrogen bond, but can it form if it has a lone pair? So I am looking at that real quick. So we're dealing with solubility, and you can, if you have a lone pair, if it's a lone pair on a fluorine, oxygen, or nitrogen. So sulfur cannot, because that lone pair will not form hydrogen bonding. This one here, the fluorine, can accept a hydrogen bond. This hydrogen here can form a bond there. List the predominant. So the predominant intermolecular forces are the ones that determine its boiling points and melting points. So we said that we have hydrogen bonding, and then we have dipole-dipole, and then we have dispersion. So sometimes your homework might ask you to list all. Well, if it has hydrogen bonding, folks, it also has dipole-dipole and dispersion. Okay, if that molecule has dipole-dipole, then it also has dispersion. So if it's up here, then it has everything below. If it's here, it has everything below. And so that's where I want the predominant. So here, this is the structure of benzene that we saw earlier. Benzene took scientist, literally Kekulé, took him 40 years to figure out this structure. I mean, here we're doing it in 2 minutes. Okay, this is benzene, it's aromatic, and so it's nonpolar, so it's going to be dispersion. Is its most predominant intermolecular forces, and those have the lowest boiling points. These have the highest. So ammonia, if you draw that structure, you see that it has hydrogen bonded to a nitrogen. That's hydrogen bonding. So that's going to have a higher melting point and boiling point. Carbon, S2, so 4 plus 12 is 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. This is nonpolar. Do you see the symmetry? So this would be dispersion. And then this one here, carbon, tetrachloride, and you can see that you're going to have a dipole. It has a hydrogen, but is the hydrogen bonded to an oxygen, nitrogen, or fluorine? No, so it's not a hydrogen bonder. Okay, so what this one is dipole-dipole, because there is no symmetry and there is electronegativity difference between carbon and fluorine. So, okay, that wraps up your talk on drawing molecular structures and doing the shapes and applying the shapes and assigning polarities and ranking intermolecular forces. There's a lot of information in this, so I would say break it up and study as you need to go.